Hey everyone, April 30th. All right, let's get right into it. Average salary excluding the minimum and maximum. You're given an array, integers. Salary is the salary of the ith employee. Return the average salary of employees excluding the minimum and maximum. Okay. Answers within this of the actual answer will be accepted. So minimum salary is this, maximum salary is this. Average salary excluding is this. Okay, so we can just go right for this. This is quite, we have to make directory. Okay, so now we're not gonna sort. All we need to do is with sum salary minus min salary minus max salary, and we'll divide it by len salary minus 2. That shall work. Yeah. Okay, so done with this. All right, we have to take a look at this one. Minimum time to visit a cell in a grid. You're given n by n matrix consisting of non-negative integers, where grid row column represent the minimum time required to be able to visit the cell, which means you can visit the cell only when the time you visited is greater than or equal to this value. You're standing in the top left cell in the 0th second, and you must move to any adjacent cell in the 4 directions. Each move you make takes 1 second. Return the minimum time required in which you can visit the bottom right cell of matrix. You cannot visit the bottom right cell, then return -1. Oh yeah, this you cannot. So in this case, there's no path. Hold on, let me read it again. You must move to any adjacent cell in the 4 directions. I mean, in this case, it's not possible because you cannot move. This one requires 2, right? And if you move here, that's only 1. You move here, that's only 1. So it doesn't, you cannot visit this. So you got stuck at this position. Okay. The minimum time required to be able to, so in this case, let's say you can move here, right? And from 1, the next one has to be 2. 2 or smaller, so we can move here. The next one should be 3 or smaller, so I have these 2, right? And next one is maybe 4 or smaller. So I may go here, or I may go here. Next one is 5 or smaller. Next one is 6 or smaller, and then 7 is smaller. But I guess you can go back to the same place. Can we just BFS this? We're at this position, right? So we'll move on to the next one. That's the only one we can move to, right? And the next one we want to move to a 2 or smaller, and then we look around. We don't want to go to a position that we go to before, right? Because that doesn't make any sense if you go back to the same position as you go to before. And actually, you might want to go back to the same position because there might be some position like these you cannot go to, you need to go around in order to hit here. Right, let's say like this is big, a huge value, so you can now hit here. Oh, can you go back? I guess you can. Yeah, imagine all of these are huge. Yeah, imagine this case. Hold on. Imagine this case. Let's say we have 1, 2, 3, right? 0, 1, 1. Let's say this is 100. This is 100, 100, 100, 100. And let's say this is 5, 1, 1, 1. Right? So you start from here, you'll go here, you'll go here, right? You'll go here, and then you go just, so that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. Just give it a shot, see if this is possible. So yeah, so we're gonna do, this is 5, 1, 100, 1, 100, 1, 100, 100, 100, 1, something like that. Yep, exactly. You can go back and forth. You can go just back and forth until you find something that can go to. Oh, that makes things more complicated. Right? I mean, if you're at the start, you have to have a 1. Okay, so that's your first move. But once you can have one move, doesn't matter where, then you can accumulate however much you want. Right? So it doesn't really matter. As long as you can go one move, it doesn't really matter. I can like have all of like 1,000, right? I can have 1,000. It doesn't matter. Right? If I have this is 1,000, this is 1,000. 1,000. Oh man, what's the largest value allowed? 10 to the 5th. Let's say this is 10 to the 5th. What's going to happen? Right? Well, this is all 1,000. Well, I'm going to go back, forth, back, forth, back, forth, back, forth, back, forth to hit, to accumulate to the smallest value that you can go to. So now we move down here, right? And then if we can go down here, I can go down here, go down here, go down here, but then I cannot hit here. So I just back and forth, back and forth, back and forth, and then I go here. So if, actually, I mean, I can even just go here. Let's say last is 10 to the 5th. Right? 1, 2, 3, 4, 5. Then the answer shall be 10 to the 5th for this one. Well, I mean, it depends. I mean, if like we hit here is 10 to the 5th minus 1. Wait, why is 10 to the 5th plus 1? Because we go back and forth, back and forth, back and forth. If I hit here is 10 to the 5th, then I need to go, which means 10 to the 5th minus 1 is here. 10 to the 5th and 10 to... Oh, that's interesting. Oh. Huh. Really? I mean, it was 1, 2, 3, 4, 5. So if I start from here, this is always odd. Like it's 1, right? This would be even. So by the time, oh, I hit here will be 100. Then over here, this will be 101. Right? Will be 101. 102, 103. So this is 103. So this is 104. All right, so this is odd. This is even. I go back and forth, back and forth, back and forth. So when I hit here is 10 to the 5th. So here is 10 to the 5th plus 1. Okay, that makes sense. But do we have to consider other situations? Well, let's say if we go here, right? So when I hit here, because this is odd. So when I hit here is 1000. And 1001. So we hit here is 1001. Okay. So now this is odd. This is gonna be even. So the 10 to the 5th, 10 to the 5th. That's interesting. Right? And we want to hit the 6. So at least we need to get to 6. Get to 5. Right? And oh, okay, DP. You're gonna try DP, which means the minimum time to reach each cell, right? If I know the minimum time to reach, what's the minimum time? So here, this position, minimum time to reach here is gonna be 1, right? The minimum time to reach this, well, this is an odd. Well, that's the only way to reach here is from here, right? I mean, you can from here, but we want a minimum time to reach this place. And the minimum time to reach this place, this is a 1. So this is even, right? This is odd. So if we go this way, minimum time to reach this, 2, 3 will be 4. Okay. And the minimum time to reach this will be, well, if we go by from here, this is going to be 5. Now we say here, minimum time to reach this, because this is even. Odd, even. So it will be 4. So this won't be 5. Minimum time to reach this is 5. Minimum time to reach this. We take a look at the up is 1. Here's a 5. So minimum time to reach this is going to be 2. When we hit here, minimum time to reach this is 2. So it'll be 3. All right, minimum time to reach this will be 3. Because this is 4. So it'll be 3. And then we go back up. We take a look again. The one above us, that is 4. So minimum time to reach this. So it's 3, right? So the next one will be 5. So it'll be 6. So what will be 6? It will be 6. Minimum time to reach this, 5. So it'll be 6. Minimum time to reach this will be 3. Minimum time to reach this, well, that's 3. So it's always going to be odd. So it can go to 7. So yeah, if this and this is not the same, if this is odd, this is even, then we can always hit 8, right? This will be 8. If these two are the same, they have to be plus 1. And then to reach this is going to be 9 or 7, so this will be 7. Okay. Well, minimum to reach this is 0. Minimum to reach this is 1. Minimum to reach this, because that's the same, so it has to be 6. And then reach this, that'll be 7. All right. Minimum to reach this, because the same, so it has to be 101. Minimum to reach this is 2. Which means minimum to reach this, we have to cancel this. It's actually going to be 3. Oh, no. Don't cancel it. It is 101. Actually, no, because oh no, yeah, it's 101. Yeah, but you have to update backwards. That would be interesting. Then you have to go through. I don't know. What do you think? Maybe I can go one path is this go. And will the other path go this? No. Not sure. Or maybe we, this is a 1, right? When we look around, we see the smallest. Because the smallest will definitely give us the best chance. Maybe we, I don't know. So I'm 0, right? So the next one is 1 or 100. I'm thinking about Dijkstra. So I say I pop 1 out. Okay? So for 1, I know it's to reach it requires 1. So okay. So at this position we get 1. Okay, we get 1 and we push 1 in. Right? I mean initially we what do we put? Can go to this or go to this. We should put the minimum time that needs to reach it. Minimum time. Now the first 2 steps. Okay, so let's say we have 1. Okay. 100 actually you cannot even go. It's because initially from 0 you cannot go to 100. You have to go to 1 first. That's the first step, right? So 1 from 1, right? From 1, now you can say no. Like I said, if you have a 0, 1, you can go to any position. So we get the 0, 1 out first, right? It doesn't matter where 0, 1 is. And then we look at the next level, right? We look at this one, look at this one, look at all the ones that's surrounding it. And then we decide how long it's going to take to reach there. I mean, because this can be reached from here or here or here, right? So what do you say? I mean, we have the minimum because we have to fit this time, right? So it doesn't really matter. Right? We have this, then we know everything's a good go. And then we can say this is 6 or 7. Come here, which says 101 based on this. I have 101. And then we come in here. This is a 2, right? But when that's the 2, when we hit here, do we look back? Or are we... Or do we first look at the smallest values? Look at the smallest values, because the smallest values will take the fastest path. Or you can say if my cell and a cell has a value larger than me, then yeah, if like here, I would say I'll never be able to get a smaller value coming from these two cells because they're all bigger than me, right? Therefore, I start from 0. I look for 1. If there's no 1, that's no go. If there is 1, I go to 1, right? And then from 1, we look for the next one. That's what I'm saying. Like, why can't you just, you know, yeah. Or like after we find a 1, then we go from 0. Now we can go both, right? And this will be 1, this will be 101. Right? It's the minimum needed. And then from these two positions, we can go to these 3, right? And from this, I can go this and this. And I set the value. This is going to be 6, right? Because 1 and 5 is the same. It has to be 6. This 1 and 1, we can go directly, so this has to be 2. And this, and then this, right? This is from this, right? When this go to here, that would be too big. So this go to here, this will be 102 coming here. And then starting from 5, I try to go to this and this. So go, this is 7. Go, this is 6. So to go to here will be 101. And from here, this is a 2, will be 101. So that's will be 101, right? And then for here, this is a 1. So actually I can go to 100 for this, right? Because this is small. This is a 2. Oh, hold on. This is a 2. So this is a 101, right? So I can go to 2 and I hit 101. And this can be updated. But if you update this, you're actually going backwards, right? And what's the point? You're already here. So now you're here. So you go here, it will be 8. This go here too big, right? And for here, this is a 101, this is 101. So go here is 102 because it's already larger than, so just plus 1. And now we have to go to 10 to the 5th. Now this is 8, so that's be 10 50 plus 1. This is a 102, that'll be 10 to the 5th plus 1. Does that work? What do you think? We hit the next level, right? And then we just update its smallest value. And then we go to the next layer, right? And for each one, we can get the smallest value. Each one get the smallest value if it's good or updated. I don't know. We want to give it a shot? Yeah, why not? I don't see anything hurt by doing this, so we can give this a shot. Oh no, it's not right. Line grid 0. Okay, dp gonna be, let's start with 0 times n for this range n. You know what? Hold on, this is an m. We shall first check if, hold on, 2, right? So we shall say if grid 0 1 not equal to 1, or grid 1 0 is not equal to 1, then I shall return -1. So if these two are not 1, then yeah, there's no path. So we get rid of that first. Okay. Then we do this. Okay. Then we will do, then we know one of them gotta be 1. So I can say Q equal to, let's say 0, 0, right? That's what we start with. And while Q temp, right, for ij in Q, for ij in Q, right? And we'll go to the next one, right? We'll go to the next one for di dj in 0, 1, 0, minus 1, 0, minus 1, 0. Okay, actually, you go 4 directions. Yeah, because you do go 4 directions. Okay, you go 4 directions. Then what? No, I don't think you go 4 directions. I think you just go right and go down. But it might be a case you can go around. But if you can go around, like why would you go back? Right? There's no point going back. I think go right and go down should be enough. Right? Go right and go down should be enough. Go right and go down shall be enough. Well, if we go right and go down, then why do we using a Q? Right? If we say go right and go down is enough, why do we using a Q? I can just go right. Right? Coming here, we look up. Everything we just look up and left. Look up and left. Right? We don't really have to. Because if we only go this direction, I mean, the argument is we only need to go right or go down. Because at any point, if we want to go backwards or go up, like what's the point? We already visited this, right? We have something, we visited this earlier. And if we go up, it's not going to be anything smaller. Or if it does, like if we go back, let's just say we go back, we can make this one smaller. All right, and then what? Because you need to reach this, you have to, yeah. I don't see any point of going backwards. Like once you established, you reach the spot, right? Once you reach the spot, it's just no point of going backwards. I don't know. That's my current thinking. I think is no point going backwards. Why would you want to go backwards? I mean, you can say that if all these are giant values, okay, and all these are small values, so you go go here, right? And you say, oh, if we go backwards, then these can get smaller. But if you're already at this position, you might as well just go directly down, unless I see what you're saying. Unless we have a situation that, let's say, look at this, 0, 1, 1, 1, 1, 1, 1. Probably need another layer. 1, 1, 1, 1. Okay, like that. Or maybe we delete this one. Yeah, I think I know. I think I know what you're saying. If we have a situation like this, okay, 0, 1, 1, 1, 1, and then we have one layer empty, 1, 1, 1, 1, 1, 1, layer empty, 1, 1, 1, 1, 1, 1. Okay, Like if we have a case like this, everybody else, I just say 100. Okay, these are all 100. That's a good case of going backwards, right? So we can say this is 1. Right, this will be 2, this will be 3, this will be 4. And coming here, then this will be 101. Right? And here, oh, but this I can go from this down. Oh, this is 1, so this will actually be 100. Right? Because 1, 2, 3, 99, 100, this will be 100. This will be 101. This will be 100. And this will be 5. Okay, now we go here. That's the problem, right? You go here. Here's a 101, so this one will be 102. This one will be 101, 102, 101. And this one will be 6. And here, yeah, then we have trouble. But I don't think if you even if you go that's a tough call. So I'm here. If I go DFS, right? I go, this is 1, this is going to be 101. And I go to the next level, right? There's a 2. This, well, because this comes down, so this will, this has to be 100. And this has to be 102. Right? And then we go next level. Yeah, the question is if you can go this way, I'll never be able to go to the left, which is quite bad. Yes, because at this position, what if at each position I can go backwards? Right? At this position I go backwards. I say I'm 101. If I go backwards, right, I can go here and here. It doesn't make anything better, so I don't do it. Okay, so at this position I go 3. This is good. Yeah, and then all these are huge. 103. This will be 104. Right, and this will be 102. Yeah, but at this position I can actually go back. No, 103 I cannot go back. But the point is, right, let me fill it. This will be 103. This will be 103. Right, 103, 103, 101, 5. Right, and then the next one, this will be 6, right? And this will be, when you push it in, this will be 102. This will be 104. So the next one coming in is this, is 6. And I look up, cannot go up. Oh, I look this, wow, I can actually get this one smaller. I can get this to 7, so I push this one in again. Right? And I am here. And then I try to go, and this I can go, go here. So this will be 100. Right? Oh, no, the 6 is 101. So this will be 101. If I push it into a queue, a priority queue, then the next pop-up shall be this will pop out, right? And then I look around. So all this will be updated, right? This will be, well, I mean, this will not be updated. 7, this will still be 100. But this will be updated, right? This will be 8. And this will be updated. It'll be 101. Maybe it is Dijkstra. It is Dijkstra. So you push it in, right? And you pop out, and the thing you pop out is the current smallest distance. And you go from here, you go to the next, right? And you update its value and you push them in. And we'll do this not the first time you reach the destination, because the first time, oh, hold on, maybe it is the first time you reach destination. I mean, the smallest come out, right? And then we'll go, it doesn't go, it will go here, then we'll go here, it'll go here, it'll go here, it'll we'll go here, 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 and then we'll hit this. Maybe, yeah, let's try Dijkstra. So DP, I still need DP, okay? But I also, no, DP is that, and I need a heap queue, right? Then we have a heap. What do we put in the heap to start with? Well, we'll start with a 0, 0, 0, okay? So I should say the time ij. All right, and then we say while heap, right? And then we get a, when to say while heap and heap dp heap 0, 1 heap 0, 2. We're talking about the DP. If this is not equal to heap 0, 0, heap q dot heap pop, that means it's not equal. So we just pop, 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 pop until we get the good one. Then we say t ij equal to heap q dot heap pop heap, right? Okay, so some gets popped out, and yeah, gets popped out. Then what? Then I look at for didj in 0, 1, 1, 0, 0, minus 1, minus 1, 0, okay? Ni and j equal to I plus di, j plus dj, okay? So that's that. Then what? If 0 smaller equal to ni smaller than n, and 0 smaller equal to nj smaller than n, okay? Now it's the case, right? Now it's the case. Well, we need to see grid, right? We need to see the grid. And we say that the grid for the ni and j, so we're going to say potential t, okay, shall equal to grid ni and j, right? If grid ni and j is larger or equal to, right? If it's larger or equal to t, right? If this, then the value shall be grid ni and j plus 1. Dude, this is so complicated. Hold on. If, right, let's say plus 1, if they are the same oddity. So how do you test if they're the same oddity? Plus, right? 1 plus 1 is 2, 2 plus 2, 1 plus 2 is 3. So if, let's say, grid nij plus t, well, I mean, if we do this way, if it's odd, right, then we can always just fit that value. Else, this plus 1, which just means this plus this, I can say int, this thing is equal to 1, right? If this is equal to 1, which means they have different oddity, then it's going to be 0. I can hit potential time. Otherwise, it's this. I can say else, if it's smaller, then to reach there, it's just going to be potential t, just going to be t plus 1, right? T plus 1. Now we have the potential t. Now we need to check. We can say if potential t is math.inf, and then dp00 is going to be 0. If potential t is smaller than dp_nij, right? That means it's worth it. Then we will say dp_nij update equal to potential t, and heap q.heap push. Heap, we're going to push this one in potential t nij, right? I'll push it in. And then if it's not, then we don't push it in, right? And then we go 4 directions. We push all of them in. And we probably also need to check here, right? If I is equal to m minus 1 and nj equal to n minus 1, then we shall return t. That means we have found it. Okay. And then go 4 directions. We have the heap, then go back up. If we come out, then minus 1. I don't know. This looks let's see if we can even pass the, that should be 7. Yeah, this should be easy to pass because I did this check explicitly. Now this is interesting. I will try this. That should be 10, 2, 3, 4, 5, right? And the last one, the one that I come up with. Actually, we can try it here to see how it goes. So how many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay. This is 0, 1, 1, 1, 1. 4 ones. And the next one is gonna be 100 and a 1. Next is 1, 2, 3, 4, 5. Jesus, come on. 1, 2, 3, 4, 5. Next one is 1. 1, 2, 3, 4. 1, 2, 3, 4, 5. How does this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, 16. Okay, let's see if this one I can get 16. If I can, then I have, more confidence, right? Grid. That's very bad. Okay. What the hell? What the hell? Oh. And dude. Come on, dude. Ew, that's ugly. That is ugly. Okay, so a little bit work needs to be done. Well, probably have to pull this one to the side. Okay, let's throw this up. Let's see how we go. Okay, so we are going to do 1, 2, 1, 2, 3. Okay, so we have 0, 1, 5, 1, 100, 1, 100, 1, 100, 100, 100, 10, no, 100,000. Okay. So, let's see. I don't even know what I'm gonna look at. Okay, we start with this, and then 0. Oh, that's now 100. That should be 100 and... Hold on. So this 100 plus 100 is 0, right? Should be this. Isn't potential T should be... Yeah, grid N9NJ is 100. 100 plus 100 is 100. Mod 2 is 0. 0 equals false. Oh, equal to 0. Right? Equal to 0. That means if this equal to 1, then I don't. But if there's... Yes, I think I got this one wrong. Okay. All right. Do we dare? Yes, we dare. Let's give this a shot. Yeah, just run this one more time. Make sure it's correct. Give it a shot. Let's see. Ugh. Okay, not good. No. Oh. Oh. I did not check. But why do I need to check additional? It says this is not possible. Why? Why would it not be possible? Because it's a 0 and 0. Oh, jeez. 0 and a 0. Oh, man. But that's still, right? If it was 0, 0, I can still go. Right? I can still go. If it's a 0 and a 0. Yeah, I can go back, and we can go. I do not understand. Because this is 0 as well. But still. Does this one work? Oh. Wait a second. Wait a second. What are you saying? That... Hold on. Let's shrink it down. Okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Does this one work? Some value. Okay. Does this work? All right, that's our case. Come on. What do we have? We have a 2, by 4. We have a 0, 0, 0. 3, 0, 3, 4, 0. 2, 7, 9, 6, 6. 5, 3, 3, 2, 1. 7, 0, 4, 3, 4. 5, 2, 1, 1, 0. And they're telling me this is not possible. Why? I mean, I'm a 0. This is 0. Which means it's okay. I can always go, right? I can just go, 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 go. This is going to be 0. Right? We start with 0. When we're here, it's going to be 1. And when we're here, it's going to be... Now this is going to be 1. Right? So when we get here, it's going to be 3, 0, 3, 4, 0. When we go here, it's going to be 5, 3, 3, 2, 2. Okay? And then we push, these come out, so this one comes out first. And then go here, it'll be 3, 0, 3, 4, 1. Which come here. I don't understand. I don't understand. I think maybe I understand the problem wrong. What if I just use like this value? Does this one work? Interesting. I think I understand the problem wrong then. All right, let's do this. Does this work? Oh, hold on. My output is -1. Wait. My output is... How is my output -1? Okay, I got it completely backwards. My output is -1. Wait, what? What the hell? Alright, that means there's a bug. I thought I understand the problem wrong. No, I did not understand the problem wrong. I understand the problem correctly. Expected is 3. Dude, why would you become... Wait, how? I start from this. Uh-huh. Well, the start will always be correct. And then go to the next one. Next one's math.inf, right? If grid is larger, you go to T. No, grid is not larger, you go to T. Grid is larger, you go to T. Because T is 0. Now the grid is 0, right? Then I say it's going to be this whatever grid plus this, and this is smaller than dp. That's true. dp with this. How would this be -1? I don't understand. Seriously, I do not understand. Oh, here. God. If both are larger than 1. Dude. You are, how should I put it? You're quite dense sometimes. Okay? You're quite dense sometimes. Yeah, but it's good because now I can try this one out. See if that's correct. Yep. Booyah! Got it. Got it. Got a little bit hiccup, but booyah! Yes. Oh, yes. Now I feel good. I feel wonderful. Dijkstra. Right? So Dijkstra is definitely the first trick, right? So we record the minimum time needed to reach each cell, right? And the next cell to visit must be the one with the current smallest time. The other trick is that if a cell's required time is not smaller, right, than its previous one, then the min time to reach it is the previous and is the required time plus 1 if the required time has the same oddity as the previous time. Otherwise, we can reach it with the required time. Another trick, the third trick, right? This is another trick. The third trick is that as long as grid 0, 1 and grid 1, 0 are not both larger than 1, then we can always visit every single cell because we can go back and forth, right, between two cells in order to accumulate time to reach the requirement of the next cell. Right, so the runtime OMN, I do not know, this is what you call it. I mean, each will be visited more than once, sometimes will be more than once. I don't know what's the runtime of Dijkstra. I mean, likely the worst case scenario, right? You'll visit every single time, and every time you have to do a heap. So this is the worst time. I just call this is the worst time. Oh, got this, man. Ping pong Dijkstra. What the hell is ping pong Dijkstra? Back and forth. Ah, it got back and forth Dijkstra. Yep. Nah, I like my way of thinking. I like my way of thinking. Right? You just like, oh, did they use the original one? They haven't visited. If it's not in visited, wait. What do you mean? Oh. Because each one visited will always be the smallest. Is that why they use visited? So you don't have to visit again. Interesting. Because if you do that, because this is just guarantee every single cell gets visited only once, right? Every cell gets visited only once. And you guaranteed when you visit it, it has the smallest time. Because every time you pop out is the smallest. But that's not how Dijkstra work, right? And Dijkstra does say you go to the next one, the smallest. Huh. Maybe that is the Dijkstra? I don't know. What is Dijkstra anyway? Visited. Yeah, they all have visited. I don't know. I thought Dijkstra always have this step, right? Well, I thought you always have this step. Now you're telling me I don't need to keep this. I can just have it visited. I mean, if we think about it, it does make sense because each time when you visit something, you're always taking the smallest. No. Because when you visit, the initial you go the smallest. Yeah. Yeah, I think this is. You only need to visit every single one once. You visit it, because when you get to start, right, and you want to have different paths, and the first path you go is going to be the smallest, right? And then you go to the next one will be the smallest, so you go to the next one, and from the next one you go that's the smallest. I was trying to figure out a way that, using the whatever their way of doing Dijkstra will be wrong. But I can't think of any. It seems like it is correct. No, it will be wrong if you add them together. It will be wrong. Because you can go someplace, right, and you go around, then it actually becomes bigger. And in that case, that one should become out first. But why would this one will work if I use the set? Because it's the first time you encounter. I don't know. I do not like this. I will just use my own Dijkstra. It has been working. It always works. It works in all kind of situations, and I don't think it's too hard to implement. That's the only thing. Well, we do have to use a DP array though, so yeah. But they have to use a set. So space complexity is the same, right? Time complexity, maybe because I have this, but overall I don't think it matters too much. Yeah, I just call this. Good. Very good. Okay, that will be it.